plate are wires that are pulling on it. And like if I were teaching, I would ask, like a relatively simple question is, which wire has the greatest tension in it, the outer three or the inner one? Any takers? There's, again, this inner one's pulling up on this bar, and these other ones, hard to see, but the other ones are pulling down on the plate. The inner one, yeah, because it's the only thing that's acting up. Gravity and all the other wires are pulling down. And when you look at it up close, you see that that's the fixed wire. So it makes sense. As it mentioned, you can tighten these wires here by turning little screws. Do not over tighten these wires because the middle one might break. Sorry? Tensegrity. I have a tensegrity table. It's red.
They also have, if you don't want to spend a lot of money, they have like for $12, you can get a Lego version on Amazon that your kids can assemble themselves.
Right.
And they're super fun. And if you get one of the ones that is blue or green, comes with a little Lego man, you can stick on it. When you get the gray one, there's not a Lego man. So if you want to have a little Lego man, if you stand on the top of the table, I think one of the fun colored ones. But the kids love them.
If anybody's a fan of, anybody watches many YouTube videos that I do of Zach King did a video of furniture, and there's an end table that he featured, like exactly like that.
Anyway, my demo here, and I don't know, Alice, if you can dim the lights. Here is the excuse me, the wireless charger. I just bought a cheap one. And I figured this has two LEDs. And right now you may see the upper red one. You should be able to see that. The lower one is in fact actually blinking. It's the blue one. But it's really hard to see blinking here. You'll notice if I lift this up, it stops dimmer at about a centimeter or two height. Excuse me. And one of the things about this is I think there's 12 turns of this wire that I made. Excuse me. And I'm going to put that back here. And I'm going to put this other one, which has 20 turns of wire. Put it on here. Can you see the blue from back there?
Yeah.
Okay, so the red's brighter. And one could, how they're connected. I have the two anodes, the long ones like this together, and the two cathodes of the LEDs together. So both anodes are connected to one another, and both cathodes. And you can see that they're blinking on and off. And I thought, well, that's probably how this works, is via some types of induction. I don't know if you've seen the jumping ring coils where you can put lights down the coil. Mine's too heavy to bring here, so. And it works on the principle of changing magnetic fields, inducing change. Actually, it's third equation down, Faraday's law. So you can see that both lights are flashing on and off. So what I'm going to do here is turn this on. And again, you're at a distance, and I don't have a big oscilloscope at home. This is oscilloscope. It's actually not bad. It's a 2-channel, and you can go. I can get good timings, less to several nanoseconds. So it's pretty nice. I think I got it for $40 or $50 online. And what you can see, and I'm gonna just freeze it. And this battery saver in this will make it go out a little bit. You start or turn it back on. You can't see the scale from there, but it's set at 100 milliseconds, so a tenth of a second is per block, and there are 4 blocks between the right side of this bar, this yellow bar, and the left side of that other bar. 4/10 of a second. And if you look at that, that looks like it's blinking around half a second-ish. So when I did this the first time, I thought, okay, that's sort of interesting. And oh, by the way, the width of the blocks, the yellow blocks, their width is about a tenth of a second. So I don't know necessarily what was going on, but I know I could make it go faster. And so what I'm going to do is increasing the sweep speed. And more. Now the sweep speed is for every block on the scope, it's 100, excuse me, what's that? No, 1 microsecond, a millionth of a second. So you can see this yellow top part, and there's another one here. The yellow top parts are on for about 3-ish blocks. 3 microseconds. And then well, I'll get to that in a second. The lower part, again, it's hard to see, is actually this oscillation. A little wavy part, and then it goes to the straight upper part, and then back to the oscillations. Remember, I mentioned that both things are connected to anodes, to cathodes. So my guess is that when the lights go on, they're on for 3 millionths of a second neighborhood. When they go off, there's an oscillation. I read about that. What I have a coil, but I have no capacitor. Well, apparently there's a referred to it as parasitic capacitance, an inherent capacitance of the coil itself. So in a sense, there is a little circuit, capacitor, coil that's resonant at about, again, see the scale. This is about 10 or 2/10 of a millionth of a second. So what's that about? 500,000 hertz. That oscillation that's there. So it's a very rapid oscillation that's occurring in the negative side. And again, both lights are on. That made sense. Now I'm going to just take this off. And oh, sorry.
What's the parasitic capacitance of the scope?
I don't know.
Does that may be a factor as well?
It may be. I'm not, but it's not a.
The scope is just from across the LEDs?
Yeah. Okay. Well, actually, the coil is across the LEDs, and therefore I have the scope. So what I'm going to do, I'm going to switch to this other coil. Oh no, sorry, I'm going to switch not to the other coil, the other capacitor. How about LED? Other LED. I'm going to put them on the one that has. And again, you should see that, right? Now, what I gotta do, this is where my shape ends. Little bit of a problem. Can you, let's just turn on so I can see what I'm doing here? No. Okay. Now you can see there's sort of the horizontal bar and then the lower part goes horizontal. It's not that oscillation anymore, right? Yes, good. And I did make a difference with these two LEDs. And this is how I actually originally had it set up when I was first looking at this thing. I have the cathode connected to the anode of one and the other cathode and anode connected. And so now, as this thing oscillates, both are going on, but to our eye, what are they going on at the same time? To our eye, there's no oscillation going on. But that again has to do with sort of what's happening with, going to go back to narrowing that to the time scale. There they come. Going back to that time scale and freeze it. And at this scale, they look like they did when I originally showed it. 2 yellow bars and the flat nothing in between the line, just the horizontal line. But when we looked at the post scale, saw that there was actually a variation going on. But our eye, this again, the bars are about 1/10 of a second of these yellow bars. That's how long the lights are in a sense on, even though they're oscillating extraordinarily rapidly between the two. I would love to have some type of way to see the oscillation going on. Oh, I looked up about turn on and turn off times for LEDs, and I read that they're in the low nanosecond amounts, like 1 to 10 nanoseconds. So that's not getting, they are going, they are going on and off and on and off, on, switching. But to our eye, they, again, we can't notice that. Now, I don't know what happened. I didn't investigate this far enough yet to see when you put a phone on top exactly what the link is, how this variation is getting eventually picked up by the phone. But that's I kind of thought it was interesting. Anyway, any questions? Sorry.
Make a slow motion.
Real
Slow motion video, you see.
again, this is that thing is oscillating in a few millionths of a second. There's no, I can't afford a camera that could
Okay, bigger coil,
have that. What?
bigger coil.
Yeah, bigger coil, right? And by the way, again, you can see when I do lift it up, it dims, but the blue one dims fast, look quicker. But it has a higher voltage, and it's not getting it, at a distance. Okay, again, that's it.
Good day, everyone. Good to see everyone today. I haven't seen some of you in quite some time. So my presentation is about drones. I've been about these drones for quite a while, and I haven't let go. So today, instead of I have large drones now. I start off with the cello, which we use for EDU, and it's all about AI. All right, so this is the Sphero robot, and we can control it using code, as well as we can code these drones as well. And we also have fellow EDU TT, which you can bring in the classroom and teach the students how to do coding with these as well. You can do Python, running, and so on. We have a problem with the Python because they're a little tired after trying to work and communicate with Python. It kind of uses up a lot of brain power. So we've been using the running, which is an easier program for coding. So that's stem cell running. We present that much more these days. So it's all about the battery. We found lithium in Afghanistan, and so we use a lot of them for batteries. Only thing about the battery is that lithium does not last long. And please not put it close to any water, because you can have a chemical reaction that you may not want. So I'll turn the drone on. So a lot of times I do these demonstrations and the battery runs out, like I said, I practice outside, I come in and I use up the battery because the lifetime is so short. Let's see what we got here. It's on. All right. And you just saw the color just flew off. It never fails. The good part about the telos is that they're easy. And the batteries run out as well. So I'm gonna try to fix it real quick and do the demonstrations again.
You said the student program, you're on, or is that just the Sphero?
They can program the drone, and they can program the Sphero.
And you said they're both in Python, is that something that they're doing? Is that something that they need, like a computer with software installed, or is that something they can do from them?
Yeah, it's installed in the program for them to be able to do Python or the scratch. They move them on up the line from easy to difficult. This red light means my battery check. Oh, it's not an oh no situation. It's a aha.
How long does it take to charge?
A couple hours. Maybe a
It's
couple
not
hours.
identify a lab.
Up to speed.
Green wiggles around, it's a bio lab, it stinks, it's a chem lab, it doesn't work, it's a physics lab.
Always have that. Okay, so I'll place the new battery in. And I'll charge this up. And you can use the Wi-Fi on your phone. Try again. Need the communication. The camera should show up on my phone, and it's not. So they're not communicating. So I have to do the Wi-Fi all over again. And this is supposed to be a real quick demonstration. But that's how that goes. Just that quick, my Wi-Fi went off, so I reconnect. Then I have a 9F. Okay. So I had to reprogram it while you're looking at me. And we're gonna try again. I think that propeller's not made to stay on.
Let's do that.
Done very nicely. Crazy move.
Well, you get all two propellers.
Oh, it's two this time.
Yeah,
So technology at work. So what they do is when you do get your tele drone, they give you extra propellers for a reason. And you just saw that reason because technology at work. So I have to redo these, but I will say this demonstration.
You can use it to demonstrate thermodynamics.
Well, there's a whole lot of physics and science behind it. So I just want you to see it in action. But here, before, this is my run leak, stem cell run leak program that you can put on the robots to get artificial intelligence out of the robot to do the coding with. And this was 2 years ago. And now this is the modern day. This is our program. So it's much less wiring and it's much faster and not as bumpy. And I don't need the big batteries like before. So that's technology at work. It's constantly changing when you do a robotics. 1 year it's one way, the next year it's another way. So with the drones, I've been using DJIs. So we have the mini drone that does inspections, and we got the 5G towers, so we need bigger drones. So we had the mini 2, we got the mini 3, and now this year we got the mini 4. And got a lot more drones out there. And it's much more work to be done with them. So with our kids, if they want a summer job, if they want to be lifeguard down on the shore, they now have the drones that go over the water, see if any sharks survive or if somebody's drowned, for example. So I could go on and on and on, but I won't. But I'll take any questions.
The little drone that you have right there, how much do you remember how much that would cost?
Well, this was just $99 for one battery. If you get two batteries, it's $120.
And what about the little Sparrow?
Sparrow was $129. I don't know what it is now, because you see this, it's not clear anymore because it's been rolling around on the floor. So if any of you in Star Wars or those kind of movies, this is the robot. Any other questions? I can talk about this all day. Come on. We don't have all day. I hope you accept my demonstration. And next year, when we have another demo, guess what you're going to see from me? More drones. Thank you very much. Thank you, Paul.
Thank you, Jay. All right. All right, so Craig is going to come up and take an old take on centripetal force table. Do you want me to give these up?
Okay, so what I did. I took a 10-Newton spray steel. Attached it to the typical old kit that comes with the washers. Put on a meter stick, take it down, there's pretty much flush. When you spin it around, you get a nearly horizontal surface, and you can measure the force to take up. You take the period of this, you can measure the speed. Because all you need to know is the radius, which you have a convenient meter stick to measure. Once you have speed, you can then plot speed squared as the x-axis, and whichever variable you vary, either the radius, 1 over the mass, or the force on the y-axis, and you can basically develop the correlation. You know the mass of the stopper, and you know the other variables, so you should find out what the slope should be. There's going to be error when you do this lab because gravity is pulling downwards. It's not perfectly horizontal. So you can actually have them find the percent error, which is basically the effect of gravity based on when you pull the stopper. The thing is, you want to get a variety of stoppers. Like this one is only a 7 grams. This one will go much more horizontal, but it's harder to get the force up. The lighter the stopper, the easier it is to get it to be horizontal. At the same time, I can make the string longer, but I'm trying to keep it. Yeah, and I have a rubber band just so I can keep it on there. You don't even need the rubber band, but the rubber band just so it doesn't slide as much. But I have it at half. I generally do it at half a meter because it's 2 pi r. So it's pi divided by the period to get the speed. And you can measure it that way. But then you can vary the radius, and I go from 30 centimeters to 70 centimeters, and then you can vary the radius. The point is, this is the lab. This is from project physics from the 70s. But the point is that most people don't know that project physics even existed. So the point is to have it. The point is to have a lab like this, instead of just the washers that you're measuring and they're trying to do that, you can now make quantitative measurements. And you know where the error is coming from because gravity is pulling down. They can actually find out the effect. If they plot it in graphical analysis, then they can get what the slope should be because they know that. They have the value of the slope of the data points, and then they can actually give you a commentary on why that is showing up. And isn't that what we're trying to get in this? You have to draw a 3-body diagram for it. They can see that you have tension going in and gravity going down, and the tension is going up at a slight angle, and you really get into a lot of physics in this when you're doing centripetal motion. And now you have a way of measuring. Yeah, Joe.
Have you found any issues with the size of the circle that the kids wiggling it in, or
The longer the circle, the more the more it drops down, the bigger the errors are. But when right,
just in terms of the stick,
the stick starts to wobble.
like,
Yeah, the thicker the meter stick, the better it goes. I have a couple on thinner meter sticks. I didn't think I brought any of those,
but I
and
mean,
they've actually
do you-
broken
do
the
you
meter
tell
sticks.
the kids to be careful not to make the stick
Yeah.
add to the radius.
Yeah. Well, I've gotten to the point where I'll spin it to show them and then let them spin it on their own. But I kind of show them that I'm holding it still, how I'm holding it. So if I'm holding it in the middle and I keep this around 50, it's why the string is about a little bit more than a meter. So that it actually, the circles, when they get too small and things like that, they're not going too far around. But again, it's the better they get at collecting the data, the better they get at spinning it, the better their data is. But if they have errors, there's nothing wrong with having error as long as they can explain where it's coming from. And again, watching them spin it and watching them do that, they start to get a sense of it because someone will be very good at holding it stationary when someone else tries it. They're going all over the place. And they say, no, you spin it. And they can figure all that out. And I have 90-minute blocks, so this doesn't take that long to collect the data. So they can actually figure out how to spin it, and they get pretty good at it by the class. And they're doing 3 different trials, and then they change for different masses. And all I did was mask them and put them on there. So it's a lot easier than having to put that. And again, just the assorted stoppers make it a lot easier to have different masses to do that. So they end up, the data for mass ends up being the least reliable in terms of when they're doing it. I don't know why, it just the masses are going from like 7 grams to 20 grams. So there might not be enough spread to actually get a nice cluster of points. And I have 5 different masses when I do it. But in general, they do get good enough data that they can analyze and talk about and see where the errors are and understand what's going on in terms of the mechanisms of the lab. And again, this is what I use to introduce centripetal motion after going through some of and deriving the equation with them. So then we do this and they can start to see how radius and period basically fit into speed and how that fits into divided by r squared. So you have the radius on the top and you have the period squared on the bottom. They can really see the effect. And when you make the radius bigger, they can really notice and they have the intuitive sense with a bigger radius and shape longer to go around. But what does that mean for the actual speed that it's going? And it really gets into a nice conversation about tangential speed in terms of all of that as well. So again, yeah.
I think mine minimize friction at the pivot.
It's a glass tube. So the string is going around the glass tube. It comes with the kit. The kit I have aligned with plastic instead, so it's smooth around the glass edge. So that works better than the plastic ones, but I couldn't find the glass tubes online when I did a quick search to give you guys a link. So those are plastic tubes, so they're not as good as the glass ones. You can find a glass tube that works a little better. But again, I couldn't find it. What?
You need to use a regular straw.
You can use the straw won't be sturdy enough in the string. It'll start getting cracked in the string.
You bury the spring like
I use
dental
it-
floss or anything.
To have enough tension, I'd be worried about dental floss and the stopper butterfly. Because you have to tie it around 2 holes in the stopper. So I'm just using a pendulum string there. Yeah.
Tried the pretty probe instead of these.
The Berner force probe makes it very hard. Makes it very hard to spin. I don't have wireless probes. I have the wired probes. So it's very hard to do that.
I think it's wireless.
If it's wireless, it might work just as well. The only thing is that you need to attach it. You need to have a way to hold it, and I'd be afraid of them dropping the wireless probe with it spinning around. With a $6 spring scale, I'm not too worried about something happening. And I don't have a problem with error. And when you spin it, you'll notice the force isn't consistent, it goes up and down a little bit. And that's fine because they can see that and they can talk about it. And if they can talk about where the errors are coming from and the inconsistencies of the measurements, we're really getting into what's going on and it gives them a more robust understanding of the situation. Yeah.
Right, it's boba straws.
No.
They're much stiffer and thicker than normal
Right.
straws.
But
that
the glass is smooth on the edge, so you
Yeah,
have very little friction as the strings burn. So the smooth edge of the glass kits were a lot better than the plastic one. I just couldn't find the link to them online when I did the search. That's what you got on the front page. But if you can find the glass kits, I think I got mine from School Specialty, and they were glass. And I think Fisher only had the plastic in the same company. Yeah,
Can't your friends at the chemistry, who teach chemistry, give you your glass, pieces of glass?
they could, but that would imply the chemistry teacher knowing how to etch glass.
yeah, that's not a good, I'll say that if you're a high school teacher, that's not a good bet.
Yeah, unfortunately, the working with glass and the cutting of glass, things like that is a lost skill on a lot of chemistry teachers. So if you have someone in your school that can do it, that would work great. But they sell the kit, it's like $50 tops. That's the most I saw online. And you just get the glass kit, it comes with washers, it comes with string, it comes with one stopper. You have assorted stoppers for $15. You have a class set, you can vary it, they can take measurements. They can really explore centripetal motion, develop a model for the equation, and develop an understanding of what's going on. Just don't spin it vertically, you'll break your meter stick in this brace. Yeah,
Not really a question, just a comment. You're speaking of the students understanding where sources of error come from.
right.
And that's pretty much at the heart of science inquiry. But how many people just find it incredibly tricky worthy when you ask students for possible sources of error and they just list them on human error?
Oh,
Most of them.
And I told them at the beginning of the year, if they said the words to me out loud, human error, I'm giving them the rest of the year.
So my point is just, things aren't perfect, tell me why, so if another human did it, how could they not make the same mistake? That's kind of what I'm getting. So I don't accept human error, but I do expect, I do accept what's going on.
It's human error. You pushed the wrong button.
So I just wanted to show you guys, and I just did this lab this week, it worked well, I figured I'd share what's going on, one of the things that I do. Because again, a lot of you don't know what project physics is. And a lot of you don't have the project physics manuals anymore because they were probably thrown out of your school years ago after the school abandoned them. So the point is that this is a simple lab. It's easy to build. You have most of the equipment already, and it actually goes deep into centripetal force if you look at it. And there are errors because you can point out the graph when you have to draw the free body diagram. Gravity is pointing down. You draw the tension horizontal. That doesn't work that way. So you can actually get into a lot of what's going on and have them even realize what's happening, which ties back to Newton's laws when you're doing it. So it really gets a lot. So just wanted to share.
The picture of that. Okay, Bill, you're up next.
All right, how do I talk to this baby?
By the way, Craig.
Yeah.
You can
Yeah,
find
and
ESSC.
does this thing come right up?
Project with the textbooks. If anybody wants to buy one, go on to the used book, like 8 books, buy it for like 50 cents.
Yeah, they actually have,
And it's like $5 shipping.
yeah, but they also have one, I think project physics is at archive.org.
Oh, is it? Oh,
Yeah.
It's free.
Yeah, it's free.
See, look at me, I would buy it.
I would buy it too, because I actually like to touch a
I
book.
like the book, I actually.
Archive.org. Oh. They should have project physics as part of it.
ARXID.
Is that?
ARXID.
No, archive, like,
Oh,
yeah.
archive.
Yeah.
There is an AR.
It's the internet archive.
I don't want it.
Since 1974, I've been going to Mount Washington every chance I get because it's the closest thing to real mountains you have east of the Mississippi. And in recent years, I've started to have to admit to my age. So last year, between a knee acting up and the weather acting up, I had to turn around. Trip up Mount Washington starts down here at the trailhead. And this is the easier route in Tuckerman, and I got to about here and turned around and came home. This is the more interesting route coming up over here, which I usually would take. So last year I kind of decided that maybe that was it. I was too old. This summer, the 30-year-old daughter of some friends of ours was in Europe hiking, decided it was really fun and said, is there anything closer to home? And of course, being the idiot that I am, I said, why don't we go climb Mount Washington? Having decided that I was in over my head on that. So it continues to be exciting. Okay, I didn't know where that was going to go. She was a rower at Duke, and I'm an old man. We had a grand time. But it took really long. And so that's what we're about to have a look at. Mount Washington is in northern New Hampshire, right here, almost in Maine, okay, about 500 miles from here. It is the tallest mountain in the Northeast. It is not the tallest mountain in the East. Mount Mitchell in North Carolina is 400 feet higher, but it's nowhere near as interesting because it's a bump on a ridge, and tree line in North Carolina is at about 7,000 feet. So you never get above the trees. In New Hampshire, tree line's at 4,000 feet, so you got 2,000 feet of alpine terrain, and it's a much more interesting place to be. Okay, so this is that same aerial picture. This is Huntington Ravine over here, which is the craggier place. This is where the extreme skiing happens in Tuckerman. The standard route goes up in Tuckerman Ravine. There's a trail that goes up here, gets you to the summit. This is considered the most ambitious hike east of the Mississippi, going up Huntington. It's about a 4-hour hike to here, and then this is a 1,000-foot scramble. You don't quite need a rope, but it's pretty ambitious. And then you've got a mile of going uphill on broken rocks and stuff. But it's really fun and it's mountaineering. So that was the route that we took. The Appalachian Trail runs along here. This is the presidential range here, which we'll have a look at in just a minute. So it doesn't go up either of those routes, okay? It traverses, you've got 11 peaks named after early presidents running north-south. This is the east face of Mount Washington here. So here is the presidential range, and it runs, you can see this whole ridge line here. This is the east side, well, here's the summit. Here are the two ravines right here. Here's Pinkham Notch, which is the trailhead. It is about 4 linear miles here, but it takes 5 or 6 hours to hike it because it's interesting enough. And the deal is, if you're 75 years old, you get leg cramps and you have to, you know, try to keep things functioning. So you bring an armload of Gatorade and some bananas and all sorts of things, okay? And you try to maintain electrolytes and lie to yourself, and mostly it works, okay? The section we're going to enlarge here is this red section, and okay, just have to keep going. So this is the same line on a terrain map that you saw on the photograph, okay? Some points of interest, there's a very challenging water crossing here, and I'll show you why that's interesting in a minute, okay? This is where the rescue shed is for Huntington. Huntington Ravine is the center of ice climbing in the winter, okay? So the skiers are over here, and the ice climbers are over here. There's a rescue cache in both of these cirques, which is a good stopping point to rest. Here is the beginning of the really challenging technical stuff, and that's a good stopping point. Here is the end of the really challenging, nearly technical stuff, and that's a good resting point. And then you come up, and then there's the summit, okay? So this gives you an idea of what this might look like. The rescue shed here, okay, this is right at the brim of that steep wall and the beginning of this trail, and that's the summit up there. You still have to walk across all of this stuff at that alpine level. You can see you're way above tree line at this point. So, because I'm an old man and it took me forever to get there, your plan on Mount Washington is kind of cheating. There's a visitor center at the top and a road. So you only have to carry half as much refreshment as you might need, because you can buy more Gatorade, you can get, you know, calories and things at the top. However, we arrived 15 minutes before the visitor center closed, and we had to race through. We barely, you know, like, thank God we made it in time. Okay, so we got enough stuff to get us back down the mountain. I did not, as I have done for the last 49 years, leave the stuff that I had carried up at the trash cans and recycling bins at the top, so that I wasn't carrying unnecessary stuff. So I got home with my 4 empty Gatorade bottles in my backpack. And I pulled them out of my pack, and I was about to throw them out when I noticed, lo and behold, some of them were collapsed. And in fact, they were collapsed sequentially. And what had happened, of course, was, being the fuss budget that I am, when I put them back in my pack, I cranked down on the lid so they didn't leak in my pack. Because God knows you wouldn't want your pack getting dirty if you were using it. And so we end up with this, okay? I had been throwing this stuff out for 49 years. And how do we, there. In 1993, at the joint meeting of New Jersey and Pennsylvania sections at Princeton, thank you very much, Freeman Dyson was there giving a talk, and he was using discarded data from automated telescopes to look into, I think, asteroid density or some shenanigan, and he made the statement that one person's noise is another person's signal. I got him to write that on a piece of paper and sign it at the time, okay? So I actually own the hard copy of this. But of course, that's what we've got. We've got a bunch of trash, which is actually a signal. Is it a signal? Could I count on it? Okay. So if we take PV equals nRT, okay, and take it at two different positions with the same stuff in the bottom. Now, can I count on this? Okay, so what's going on the right-hand side here? N is the number of moles of gas, the lid's cranked on, so that's true. R is a constant, T is the temperature. I was extremely clever in that I took so long to go up the mountain that the warmer temperature at the low end, okay, had turned into the temperature high up on the mountain 6 hours later. So I pretty much had constant temperature, right? So I have been clever in that regard, okay? The other problem, of course, was I didn't realize I was doing an experiment when I was doing it. So that means I have to go back next year, all right? So, you know, we'll see if we can get a grant for that. But the upshot is that assuming that the right-hand side is constant, it's going to be the case that P1 V1 equals P2 V2, and that therefore my pressure ratio is my inverse volume ratio. Okay, but now how can I relate that to elevation? As we all know, there's some annoying exponential crap going on out here, but Mount Washington is comfortably not terribly high. And so here's Mount Washington, here's my curve, and look at how close to a straight line it is up there. Why, son of a gun, that's got a constant slope. Which means that I've got P equals negative Ka, H, right, here's my pressure, here's my height, it's a downhill slope. So that would mean P1 over P2 equals H1 over H2, ta-da. Okay, we get this, we get that, okay? And so I should be able to determine height with the volume ratio of my Gatorade bottles, okay? And so, yeah, so this is, here's my elevation, and I use feet, I understand, you know, but I'm an old guy and we used to not be metric, okay? But the other point is that feet are really what people think about on East Coast mountains. And so we can calculate the atmospheric pressure, okay? And this was pretty close to what we had during that time. So at zero elevation, it's 101.3 kilopascals. And as we go up, we get this. So we could almost just move the decimal point, but not quite, okay? Because that's not 100, it's 101. And so our pressure ratios look like this. When we do the displacement, and let me go back. Can I go back? What do I need to do? Yeah. So I was doing displacement this way, where I had an old calorimeter thing, and filling it with water, because if you notice, the shoulders of the bottles are stiff enough that they don't distort, okay? So I really only had to find the volume of the lower parts of the bottles. And so I could determine the volumes of the bottles compared to the volume of a bottle that, you know, had not been sullied. And so we end up with a volume ratio, or I'm sorry, a pressure ratio graph here is the red line, and the volume ratios for the bottles, which should be the same, I placed on the line. And that lets us determine an elevation if we work back, okay? And so if we do that, we can place this on the elevation map. And some of this is, it doesn't explain as well as I'd like it to, okay? this was not very far, not very strenuous. So this, I think I was trying to gulp a bottle as I left just to get some fluids. And we very well may have done this. As I say, I didn't know I was doing an experiment at the time. But up here, we've got, okay, this bottle is right about at the point where we stopped. And this was a point where I was dealing with some serious cramps, and it was questionable, like going either way was going to be annoying if my legs weren't working. But it turned out the banana and the Gatorade worked just fine. And so this is about right, although I think one of the bottles we emptied up in here. As I say, we've got to go back and do this a bit more clinically. But the reason I'm telling you this, okay, I know half of you don't give a damn about mountain climbing. People carry water bottles around all the time. And they, now when a kid says my ears pop, you can say, do you know why? Okay, take a water bottle. When you're in this area, take the lid off, empty the bottle, screw the cap on tight, bring it home and see what it looks like. Okay, there's not as many air molecules as there were in the other place. And your eardrum is doing just what that bottle is doing. Okay, we can actually see that. You can play with temperature. A normal balloon is an annoyance in that it's latex, it stretches, and it stays tight. People can't see the temperature affects volume. But Mylar balloons are not elastic. And so Mylar balloons are a great way. If you inflate a Mylar balloon in a warm room and take it to a cooler room, it goes flat. I have actually found that, Wawa milk bottles taken out of the refrigerator and left on the counter inflate. Okay, so there's a lot of stuff you can do with water bottles, Gatorade bottles, etc. This is a really accessible way to play with the gas laws. And, it's a kind of interesting thing. If you have a student going anywhere interesting, tell them to bring home an empty water bottle that they capped at the elevation and see if you can think about it. Let's see. Wake up. Okay, yeah, here's the money shot. The old man actually did get to the summit. Okay. And what, this is, I'm going the wrong way. Okay, and this is some of that climbing on that slope. So, it's interesting. It's really a lot of fun to be there. And I was looking. There we go. Because I had a bottle that I had done when I climbed Mount Whitney years and years ago, and thought it would be, and I thought I had it in this list, but I don't. I took a water bottle, a flexible, the old kind that was going to give you all of the nasty chemical outgassing, and capped it at the summit of Mount Whitney. That's 14.5, and that sucker really collapsed. Okay, that's a kind of a dramatic thing. And I thought I had that picture of it, but I don't. But it's kind of an interesting thing and dramatically visible. And of course, now that everybody carries water bottles everywhere, and water bottles are wonderfully deformable. It's something that you might suggest that people do a project where kids want to do. That's about it.
You know, similar experiment, the planes are pressurized about 8,000.
Yes, exactly.
So the tangent back are
Mhm.
exploding.
Yeah. Yeah.
That's not why they soda bottle release, like in this area.
Okay.
Apparently Diet Coke is the worst if you want your flight.
So how did you get down?
Well, you come down on the other side. You come down the Huntington or the Tuckerman side. But that was interesting too. We were so late that the last 2 hours were in the dark. This was just beginning of September that we were there. And it isn't an adventure if you're not walking out in the dark. Yes. what you do is you come around and we were coming down, that's the steep part. I've been up that probably 40 times. I've never come down it. And they've got signs all over the place. You'd be a fool to do that. So you go over the top and come down this side here. That's avalanche prone in the winter. In the winter, you come down right here on this bridge. That's the Lionhead Trail. In the winter, it's a real case.
It comes out, right?
Yeah. No, you wouldn't want that. That's cheap.
You said there's a road up there.
Yes, it's an 8-mile road that goes up, all the way from way over here. And when you come up, you crest, and there's a stop on the road right there. So there's people driving up that see you coming up over the top and wondering.
So for those of us who are not capable of finding around.
Right, you can still do this, and you can stop at different levels. And the neat thing, the Mount Whitney bottle that I had was a single case. And see, this is the process. Like, this is to say, not just that, look, the equation worked once. This is to say, look, we understand the process. We have a thing that's going on, and the variables follow law. And that, I think, is a real addition to the process and an important insight to get this. They're not. I'm sorry.
The next generation science standards
Don't include gas laws. We've got to change that.
All right. So you think about numerical trajectories and integrations being very complicated, something they do at NASA with supercomputers and stuff, but it's actually not that difficult. Something that students can approach pretty easily. I'm going to show you that today. You're on the screen, you're sharing?
Yes.
Okay. It'll zoom away in a minute. All right. So let's start out with the first simple thing we can do. Apparently moving the screen is not a simple thing that I can do. Is there? Okay, so how do you do it? That's this thing you point at my eye? Is that how do we do that? You just over there, you gotta use those things. Okay, so the equation on the left here. When I teach physics, intro mechanics, the first equation is equals VT first day. Third equation, fifth day. And the second equation, Newton's law, third day, and the fifth day, and the third equation by the third day of class. So, it's basic kinematics stuff you're doing. Now we convert those from straight up equations to difference equations. So we're looking at, imagine we have a time step. That's a small increment in time, and I'm going to advance the position. I know the initial position and velocity. I'm going to advance the initial position and velocity by some small time step using the equation of motion. And so one way to do it, we say, well, I have my position. I take the velocity times my time step, add it in, and I get a new position xi. I've made the old positions in blue and the new positions in red because they say that you got to inject color into your slides. So you can see how minimalist this is otherwise. No distractions, but so that's the color there. So blue is old, and blue is the old ones, red are the new ones. And we get to purple later. That's the intermediate stuff. So very easy to do. You set up that equation. Now you can't just throw it out. If I leave it at that, then my object would just drift off into space at constant velocity or move wherever it's going. So there's no point in doing that. So we have to apply a force as well. So we would calculate the force and assume the force is based on position, like it usually is around the gravity field. The example I'm going to do next is the balloon and the Earth. I didn't draw them to scale, but the graphs are to scale. So I've got Newton's law, and you calculate there's going to be an acceleration based on where you are, the field you're at. And it can be gravitational, it can be electric, it can even be magnetic, but there's some complications to that I'll get into later. And then you take that acceleration, multiply the time step, add it to the old velocity, get the new velocity. Very simple equations. You can implement them in any language, programming language you want, write a computer code, have it run. And if you do that, you end up with this. And let me test against the advanced ones. There we go. Yeah. So start out, the small black dot is the moon, the big black dot is the Earth, and you start out and let it go, And I set this up with the correct average moon, Earth moon radius, big G, and the values of the mass of the two. And you start it out, and the moon spirals out and goes away. And observationally, though, during my own life, this doesn't happen, right? So there's an error in the process, and the problem is that the method, the integration method you're using, just stepping forward like that, gives you this error that gains energy. So maybe the problem is in that process. I'll go back a slide. Look at this. The first equation, the original equation, d equals v average t, and I'm taking the initial velocity and not the average velocity. So that's part of the issue, and so it's comparable issues on the third equation. That's the problem there. So moving forward, suppose we did something a little different. Oh, let's go back before we do that. This is what's called an explicit first order method to do this, and you get some errors that are built into it. You could change the method slightly and go to an implicit first order method. And now we're looking at our new position. Xi is going to be xi plus 1 is going to be xi plus the new velocity. And likewise, the force is based, the acceleration based on the force is based on the new position. So instead of looking at the beginning point, look at the end point. You might say, well, that's tough because we don't know the end point. Computer programmer would say, I can't do that. I can't solve that equation. Mathematician would say, oh, we can do this. There's a way to do it. And the trick, consider, for example, a harmonic oscillator. So F is just minus K over mx. You can then solve the equation, put all the x plus 1 terms on one side, or v plus 1 terms, so it's not the acceleration, on one side, and divide it out and solve. You get a fraction in the bottom. And so the math is a little messier, but it's quite doable. This is an implicit method to solve. This is the implicit first order method. You can't see the titles because they're blocked by the Zoom screen. And if you do that, you get this. Nope, this. And it spirals inward. I had to actually stop the simulation early because it eventually crashed into the Earth and then did a little loop-the-loop and then shot out into space at a 45-degree angle. And again, I know the moon doesn't do that either. So again, this is wrong. So the problem is we're losing energy here. The system constantly loses energy because we're taking the end points instead of the beginning points. So you might think, we need to mix them somehow. How can we do that? Some sort of average of the two. And it turns out the easiest and the most mathematically correct way to do it is to just do a semi-implicit method like this, where I take, for example, I use the old position and the old velocity to get a new position. And I use that new position to calculate the new velocity. So I'm using the old data for one part and the new data for the other part. And that's called a symplectic method. This is a symplectic first order method, and we're doing drift kick. Again, you can't see the titles, but the idea is a drift is when you let the particle propagate through space or whatever based on the velocity, and a kick is when you change the velocity based on acceleration and the forces that act on it. And if we do this and use that simple method, you get, no, wrong way, that. So it looks nice, very tight. And this is only a first order approximation. So we're just getting started here, first order approximation. What does that mean? If I increase the time step, if I decrease the time step by a factor of 10, I cut down my errors by a factor of 10. So I set this up so that it was 100 time steps to go around the orbit. The way I set up the simulations was I put in the position of the moon, started at 0 and the radius for the x coordinate and 0 for the y coordinate, and then give it a velocity that I calculated based on using the force balance. You can ask Craig about how to do that. There's a way of spinning around stuff and forces, balance it up, and then it should go exactly around one circle in 100 time steps. And I ran 2 full time steps to show what happened, because you do 100 time steps on the first one, it doesn't quite make it around. And the second one, I had to cut it down like 50 before it crashed into the Earth. So it's 100 time steps, we go twice around, and it maps very nicely into that. But first order means that if you decrease the time step by a factor of 10, the errors go down by a factor of 10. In a bit, we'll talk about second order. But first, the next thing I want to show you, that's a symplectic drift kick method. You can see the title on the graphic. You can also do it the other way. That would be this one. This is kick drift. So first we calculate the acceleration based on the current position, the new velocity based on that acceleration, and then calculate a new position based on the new velocity. So we're updating, and again, the blue are the old, and the red are the new ones. And you do that, and you also get a very nice result. That one, it's even tighter. If you go back to, you can see there's a little bit of wiggle in the circle at the top. There's a gap there. What's happening is, as you start out, your very first step is a drift, and you go like this, and now you're off the circle of the radius that you're moving on by some small amount. And then the gravity force is a little weaker out there. And so you get some error that's introduced. When you do it the other way, you start out here, you have, your first thing, you should change the velocity back from there to there, and then you drift, and you kind of end up around here. You actually end up a little farther, because you're following the chord length instead of the arc. But so there's errors inherent in the system, in these methods too, but at least they give you reliable, repeatable results, and it looks like what it should. Mathematical analysis is that a symplectic method gives you global energy conservation. So at any point in the orbit, it's not exactly the same energy, but the errors that add to it in one point subtract in the same way at the other point, and they cancel out, so you end up with long-term energy conservation, which is a really nice thing if you want to track something for more than a few orbits. And the mathematics behind it is too long to explain in 15 minutes, so I'm not going to try it. But you can look it up, and Wikipedia has an excellent page on symplectic integration if you want to follow up on that some more. So that's symplectic, and you can do drift kick or kick drift. Either way, they both work fine. And this is the kind of thing that you could set up as a project for an interested student, a talented high school student or a college student could probably do. And, you know, you think about things like the recent mission to the asteroid Bennu that just dumped its stuff in the Utah desert, and you got it all. Bennu and another asteroid, Apophis, both come very close to the Earth. They sort of fall between Earth and Mars orbits. So you can imagine building a complicated project where you've got the sun, you got Earth orbiting, put the moon in the system, throw in Jupiter, maybe Saturn, and then throw in these asteroids. Watch how it progresses, see what it does over time. It wouldn't be exact for a long time because, again, we're first order methods here, but it would work okay, and you get something interesting. Now, you can continue the analysis. That's the wrong way again. There we go. Leapfrog methods. If you want to do better than first order, you do a leapfrog method. And the idea here is that when we do the first two methods, the first order ones are kind of like taking a derivative. We're evaluating the velocity. And the first one, if you look at the normal derivative definition, the one over there on the first line of equations on the left, f prime is f of x over h. Or you can take f of x minus f of x minus h over h. If you take the limit as h goes to 0, the first order doesn't matter, the errors go away and you get an exact result. That's just typical calculus stuff. You don't need that to do this, but it's, if you understand it, it's comprehensible. You can also take what's called a central difference. That's the lower equation on there. X plus h minus f of x minus h divided by 2h. And the nice thing about a central difference is it's second order accurate. So if I decrease my time step by a factor of 10, the errors go down by a factor of 100. So you can get much faster convergence. If you want to know where Jupiter is going to be in 300 years, it's very helpful. You don't want to have to do a first order method and calculate to, you know, the fractions of a second for 300 years. So, so the leapfrog method draws on this idea. And the way it works is you start out with, it doesn't matter which one you use, either position or velocity, and give it a half kick. That's the one on the V there on the bottom. So you get an intermediate velocity. Then you do a full kick, a full drift on the position based on that velocity. Then you do a full drift, a full kick on the velocity based on that new position. You repeat this indefinitely. And you get second order accuracy out of that with linear equations, which is really nice. But the problem is for that method that you don't have the velocity and the position at the same time. So you want to calculate the total energy of the system, it's not trivial. So the modern treatment is to do a half kick or a half drift, and then a full kick or drift, corresponding one, and then another half. And then you do another half again the next time. And it's very little more computational overhead. Usually these problems, unless you're doing a very simple scenario, the acceleration calculations be very difficult. if you've got, say the Kepler problem, you've got 8 planets and the sun, so they're all in different positions, you calculate everything, so adding that up is complicated. Once you do it for the half kick, you can use that same position, because you haven't moved yet, for the next half kick, so it doesn't cost a lot more computation. And that's a basic leapfrog method, and a leapfrog method would look like this. Nope. Yeah, that is it. So I do a half kick of the position, then I do and I calculate the acceleration at that point, calculate the velocity from that, and then do another half kick at that velocity. I'm leaving out the line of calculating the acceleration at this point. So again, accessible to an undergraduate student or a talented high school student. And that is that would be a drift kick drift method. And then the next slide is a nope, wrong way. That's kick drift kick. They both work well. They have their advantages and disadvantages, slight differences. But that's pretty much how the method works. And these are symplectic methods. They conserve energy over the long term. And the only problem with them is that you end up slight phase shifts. The timing isn't quite right on the orbits. So again, if you want to know where something is in 300 years, that makes a big difference. You want to try and minimize that. There are other techniques you can use to do that. For example, the phase shifts for drift, kick, drift, and kick, drift, kick are opposite. So you use combinations of them to balance things out. Those are the tricks you can play. Now, the research I was doing over the last few years was about including magnetic fields in these problems. And you can see that would be an issue because the acceleration for a particle or magnetic field is dependent on the position and the velocity. So you've got more variables going on. And we worked out a method, my research team, the group I'm working with, to do this. And we used the same idea of mixing an implicit and an explicit scheme. So for the first step, we're giving a half kick to the particle using the new velocity at the half kick and the old position. So you can see that purple. So that's an implicit equation. We have to solve that. And again, I could go over the method for how to do that, but I don't have another hour, so I won't do that. It will be in the paper when it comes out. And I'm hopefully going to talk about this at the winter meeting, AAPS winter meeting in New Orleans. And you're all welcome to come join me. We'll have a big party and have some beignets and whatever else they do down there. So you do an implicit first step, half kick, then you do a full drift, and then an implicit and an explicit half kick. That's easy because you're just applying the laws. But the implicit part is the tricky part. And I have a brief description of how that works, but it won't help you. And this is the part that might be beyond a high school student. So the magnetic interactions are linear in velocity, which is nice. So you take a system of equations and you're working in 3 variables, reduce it to a matrix, and then you can invert the matrix algebraically. You can solve for what, given the input variables, you can solve for what the inverse of the matrix is. And then knowing the inverse of the matrix, you can then apply it to the known vectors to get the new vectors. And it's workable. I've seen papers as late as 2011 where a group wanted to do an implicit method on magnetic fields, and they literally solved the 3x3 system of matrices for every time step. So it runs really slow, but it gives us good results. This runs much faster and gives as good results. So we built on the work of a lot of previous researchers to do that, and we've solved this problem. It gets great results for magnetic fields as well as gravitational electric interactions. I did one simulation where I took threw an asteroid around a body and let it run for 100,000 years of simulation time. It took about 4 days. I put it in the background on my computer at work and went over home over the weekend. And I actually miscounted it. It was actually 997 years, but stayed right on orbit. The energy was conserved. Everything was beautiful. So you can get really good results out of methods like this with very simple linear equations. And it's something that I don't think enough people know about, and it's something that's easy to do. So I thought I'd share it with everyone. So thank you. So, and these are my collaborators, Dr. William Condro, Ben Richmond, and thanks for your attention. Any questions?
Can you get the solar system very centered to 100 meter accuracy?
No, but if you have that data, you can play around with it. And as a brief aside, I'll mention the reason we want to do this project, we started out by being interested in the space debris problem, space debris in low Earth orbit. And we thought, well, suppose you take that debris and you put a charge on it. Now it's moving in a magnetic field. And your velocity, orbital velocity is 7 kilometers a second, that's pretty big. Gives you a significant magnetic effect. So it might curve your orbit, perturb it, and see if you can get deorbit objects with that. And so we're thinking about that. We're still doing the analysis on that part. But we're pretty sure it'll work on really small things, and we're pretty sure it won't work on really big things. So the question is, where's the line? So we'll see. That was the motivation for this research. So any other questions? I was that clear and concise?
Yeah.
Awesome. Cool. All right, well, thank you.
Hello, everyone. My name is Andrei Blinkouski. So I've been working for Penn State, Abington. So I'm mostly teaching introductory courses, physics, calculus-based physics, so for engineering. So, and today I'd like to tell you about the interesting project we're doing at Penn State, Abington, and my personal involvement. So for the first time, we try to teach math, physics, and engineering together. And in particular, I'm going to focus on the development of integrated curriculum in mechanics and first calculus. This is what I personally was involved. So, what this NSF STEM project? So, this is 2 years ago. We won a huge grant. So you can see this big amount of money, $750,000. Unbelievable, right? It didn't make us rich. Don't get it wrong. So mostly all this money goes as a scholarship for our students. So that's why it's STEM, S stands for scholarship, right? Scholarship. But the ultimate goal is about integrating teaching of mathematics, physics, and engineering courses to improve retention of engineering students at Penn State Abington. So this is a huge project. A lot of people involved. We have one principal investigator, 5 OPI, is one of the OPIs. So we have many other faculty members involved. We have professional advisors involved, peer mentors, faculty mentors, learning center. We have collaboration with our representative of different industries. So last time, for example, we had in the profit marketing in the project, which our students was very exciting. So again, a lot of things happening within this project, but the core of this project is to teaching 2 integrated courses, 2 pairs of integrated courses. The first one is integrated course in Calculus 1 and mechanics. And the second one is integrated course in electricity, magnetism, and circuits and devices. EE to 10 is a Gatorade course for electrical engineers, and this was our thought from the beginning, that at first teaching physics and mathematics will help our students to acquire solid knowledge in both calculus and mechanics, and then from teaching together electricity and magnetism and circuits and devices will help them with easy transition to engineering courses. So this is a big idea behind this NSF grant. So, so this is a big question. It will be helpful. Right? So how our students will benefit from this, right? So ultimate goal to increase retention rate, graduation rate, so increase the sense of belonging for our students, build the engineering community of campus. So again, a lot of goals need to be accomplished with this NSF grant, but I am particularly going to talk about my personal involvement with the work of this grant. So in teaching together mechanics and calculus 1. So this is technically what is called the virtually integrated course, because we still preserve the normal topic load for both courses. So our students still technically complete 2 courses separately. But again, idea is if we teach them together, how is it going to help? So we decided to develop integrated curriculum. So we actually mix the topic and teach both courses as one single course. So this is a 9 contact hours per week. It's a huge lot for our students. So we need met 3 times per week, Monday, Wednesday, Friday. So total 9 contact hours. So it's in person. Both instructors were presented. So we both work all 9 hours, and it's constant mix of topics. So it might be first hour topics in calculus, and second hour topics in mechanics, and again topics in calculus. The ultimate goal again to make sure that our students benefit from this integrated teaching of both courses.
So this is just for lecture, it's not the introductory lab.
So let me explain this. So we actually teaching our courses is like studio-based style courses. So it's just small room, 24 students. 24 students. So it's like when it comes to physics, it's just everything all together: lecture, lab, recitation, and again, it's give you huge flexibility. You can mix the topic. You can start in the middle of the lecture and show them some simple examples, and after that, show them demonstration, do lab, and again get back to the lecture, and so on and so on. But now competition, the calculus also involved.
Just to clarify, so I'm understanding this right, it's basically one, it counts these credits in classes, but it's really one class that they're signing up for. You know, so like you don't have students that are just coming in for the math class or just coming in for the physics class. Like it is one class session where it's bouncing back and forth between the 2.
Exactly. Even though formally on that transcript can be depicted as 2 separate.
But when they're registering for it.
I mean, this is a problem. In the past, how we actually for this course, we always expect our students taking calculus physics to know already calculus. Right? So thanks to Abington, they actually can take this course concurrently. Right? So, but everybody who very involved in teaching of undergraduate courses, you probably know. You don't retain knowledge of calculus. It's very abstract when it comes to physics. They don't remember, so you need to do some mathematical review. And it's still confusing because they don't know how to apply calculus to real physical situations, so on and so on and so on and so on. So that's why the idea was without distracting our original courses, how we can combine the topic, teaching them together in one class, during 9 hours per week, right? And teaching both physics and mathematics, and ultimate question, it will be beneficial for us. Right? So this is what we do. So actually, last fall we run the first integrated course in physics 211 and math 140. So actually worked with my great colleague, John Andrei. So he was responsible for the mathematical part, so I was responsible for physics. But actually we developed the course and curriculum for this course together. So we constantly meet together, so we decided, okay, so what again we do? So what would be the sequence of topics, right? So what we need to emphasize in each topic, right? So it was really interesting experience, I have to tell you. So I mean, when you've been teaching regular courses for years, you just become tired, you know. So and this is like a unique opportunity to do some things differently. So this is why this experience was really exciting for me, right? So again, at the same time, we still need to cover the same topic that they usually cover in regular courses, And in regular courses, in Math 140, we usually follow this well-known book by James Stewart, right? You're probably familiar with this book, a standard book in Calculus 1. And in physics, we follow the fundamental of physics by how they rested more. So it's probably also well-known book. Right? So you probably, I mean, I believe majority of you are already familiar. This is quite standard textbook, so this standard set of topics. For example, in physics, it's like first 3 chapters about kinematics, right? Chapter about vectors, chapter about dynamics. There's law of conservation of energy, linear momentum, right? So then rotational motion, right? So the acceleration and all that stuff, right? So the question was how we can build everything so the students can benefit from both courses simultaneously. So the big idea is that at first, of course, they need to learn derivatives, right? Differential calculus. So because in mechanics, in calculus-based physics courses, differential calculus will be used immediately starting chapter 2. So that's why the first roughly third of the course, so mathematics course dominate. We keep the physics a little more. It's just introductory topic about conversion of units, significant figures. We do some lab about uncertainties and anything. So, but once the students have mastered their core topics in differential calculus, they immediately exposed to the topics in mechanics, one-dimensional kinematics. This is when they, for the first time, can immediately apply their knowledge of differential calculus. So this is, and later in this chapter, well, they're going to apply the knowledge of differential calculus in 2 and 3-dimensional kinematics, right? So again, they just learn differential calculus. They immediately see application. So this is the beginning. At the same time, parallel to the kinematics in physics, so in Math 140 courses, students are exposed to other further application of differential calculus, like in chemistry, biology, right? So overall, it builds a huge impression of the different application of differential calculus and derivatives. We also in physics, I particularly found this useful to add more challenging topics. Usually, for example, when it comes to one-dimensional calculus and regular classes, we just show the example involving the derivatives of polynomial functions, right? But what about exponential functions, trigonometrical functions, right? So that's why I personally found it useful to add, for example, some topics from oscillation immediately in the chapter about one-dimensional motion. So this is a great application of derivatives, right? Oh, okay. Sorry. So similar. So then we go kind of in parallel in 2 topics, and finally, when the student learns topics in integral calculus, we immediately start topics about work and potential energy mechanics, and then it will be topic about center of mass of solid bodies, moment of inertia. So again, they exposed to different ideas of integral calculus in mechanics. They immediately see application of calculus in physics. Right. And at the same time, some topic in calculus, for example, net change theorem or average function, reinforce their understanding of mechanics early topics in kinematics, or how we derive the kinematical features. So overall, again, so this is a great experience. I can actually show you just briefly. So actual weekly schedule of topic. This is how we proceeded. So topics highlighted in blue represent physics. As you can see at the beginning, mostly calculus dominates, right? But then again, so once they finish derivatives, immediately I intervene with topics in one-dimensional and two, three-dimensional kinematics. After that, again, so we kind of separated. So this in mathematics, they mostly focus on integral calculus. But once they finish, I intervene with a topic about work energy, potential energy, so moment of inertia and all this stuff.
I see there's fewer exams in here than if they had two different courses. Are the students happy about that? Yeah, but it does seem like there are fewer exams.
Yeah, to be honest, we actually discussed, it should be one single exam or still like several exams, for one for physics and another for mathematics. But because at the end of the day, it will be 2 grades for 2 separate courses to be separate. But we involve, for example, in exam, math 140 exam, we include the problems related to physics, for example, finding the right? So, yes, we need to find derivative, but it has physical meaning. So again, so this was great experience. So I'm really excited to be involved and do things differently. It's just this is just what I wanted to share with you. Thank you very much. Oh yeah, sure.
So you mentioned that you're doing this through the engineer. Are most of the students that are taking this course engineering majors or hoping to be engineering majors?
Yes, mostly engineering students, moreover, mostly mechanical engineers and electrical.
And is this the first year that you're doing this integrated course? Or
Yeah, so last fall it was the first year, first combined course. This fall, the first cohort of students is supposed to second pair of combined courses.
Transfer, that's that.
Continue for 4 years.
Oh, I think it was because I think I'm confused that it's very, actually the way that why after that they're learning and they're applying that way. But it was using our required to have to enroll into the one course. What was those?
So far it's got very promising results. So our retention rate is about 90%. So compared usually it's 70. So far it's very promising, but again it's research project. So I keep our fingers crossed, so but nobody will know what will be the end.
Realize this is the 50th year I mean, 19th, yeah, back in the 70s, a lot of the AAPT meetings were at Baldwin School or Harrison High School. And so 50 years, I think it's a century. A long time. Anyway, it's hindsight. There's something projected up, but don't look at that for a minute. I want to concentrate on this. A lot of like to teach in electricity, the relationship between voltage, current, resistance, Ohm's law. We probably do it 50 different ways. And every year, mostly within high school, but every year, I looked at what I did and I was thinking, I didn't do that. What are you trying to teach when you work with electric circuits? When they're dangerous, things can work, batteries. So a lot of this teach, I guess, Ohm's law by just saying, well, vary the voltage, see what kind of current it generates through some sort of a load resistance. And for years and years I did that, but one battery, two batteries, three batteries, put them up in series. Students put them together, they kind of see that when the batteries in the series is like more battery. Well, that was one way. But when I taught ninth graders, they wanted to burst around and play, so I was burning up batteries left and right, or batteries would be reverse connected, there's like 100 ways you could connect. So I thought, well, it wasn't terribly dangerous, although it didn't smell good after you burn out a few batteries. But what are different? Well, you could use a, crank, like a variable voltage generator. That's all voodoo. And we were talking earlier about how to keep experiments simple enough so someone sees the concept. How do you build a model? So I realized, especially teaching ninth graders, that instead of talking about, volts and current and ohms and amps and cool out there, so I had a bunch of big cans. So I had a can pre-drilled with a couple of holes, and I said to the students, mostly ninth graders by this part of my life, fill the can with water and predict how the water is going to exit these three holes. Well, that wasn't threatening. I didn't burn up batteries, didn't smell too bad. I had water all over the floor, but so when you look at something like this, most students would kind of look at this and say, well, if you've got water in a can, oh, and I had some tape across here, so you pulled across the tape, make a prediction. And almost everyone said, well, more water is going to come out of the bigger hole. So there were 3 pre-drilled holes here. Why? I mean, in words, why? Why would more water come out of the bigger hole? And interesting answers from all over. Kids I taught at West from all over the world, actually. And someone said, well, the New Jersey Turnpike's 8 lanes, not 2 lanes or a gravel road. More cars can go on a wider road, so more water is going to come out of the wider. Oh, that was nice, great logic. That was great. I said, so over time, what's going to happen? Well, everyone knew you always started out with a certain water level. If you didn't keep it pouring in water, what was going to happen? The water level dropped. Okay, sort of like the voltage without mentioning that word. So what happens over time? Well, less water is likely to come out of all 3 holes. Why? They didn't necessarily know the word pressure, but it was sort of intuitive. As the water level drops, it's less oomph, less push. So if I had 3 different holes, it was more obviously that more water came out of the larger hole at first compared to the smaller hole. But as the water level dropped, less water came out of all of them until all the water was gone. So that wasn't very controversial. I mean, they all kind of intuitively saw that. I said, okay, they feel pretty confident in that model without getting too fast. No, there was nothing very sophisticated. So how about with electric circuit, Ohm's law? So what's the equivalent of the height of the water? Well, what we call voltage. So I could put in 1 battery, 2 batteries, 3 batteries, and I thought, well, it really stinks at the wall, burning up batteries. So I thought, how about using one of these little hand generators? It's love, especially ninth graders. If there's more motion, there's more stuff, they don't fall asleep. So the faster you turn it, generate more oomph, it's like more water. But then when you're trying to measure the current coming through a circuit with like a meter, and you're looking at the meter jumping around, just like Mark or Craig's little force meter jumping around, it's great because your eye averages. So you might want to put in some sort of a sense. So let's say we have a circuit here, and I just threw this together, but I didn't want to get too complicated. So not a very expensive way to vary the number of batteries. After you turn it, here's my can. Oh, it's warm. That was interesting. This big capacitor. And then I don't have to
worry about what this is, but it's acting like a can. And it's sort of storing whatever comes out of here. So I'm gonna throw the switch in this direction. So this is connected just to this. And as I turn it, I can feel it resisting too. So I'm filling the can with water, right? Filling the capacitor with electrons. All right, so what I've done now is that can is full of water, but there's no hole, so the charge or whatever you want to call it, that's nowhere to go. So there's nothing really happening now. So I want to connect this capacitor to something. And I have the kids usually wind a micro wire, 10 feet, 20 feet, make their own resistors. Something that the stuff that stores the capacitor is going to run for. So that's what I've done right here, but let's do it live so you don't get too excited here. I'm going to suggest here on the vernier sensors that I zero both sensors. They should be zero. They've been sitting here for an hour. And what I'm going to do is to say, let's collect data. And I'm not going to worry about what's on the table here, but I'm measuring the height of the water and how much water is coming out of the can. So I say, all right, collect data. I don't want to get too sophisticated with how this stuff works because I wouldn't do this like with ninth graders without a lot of explanation of what we're measuring. But there's like Ohm's law in 5 seconds. With a little technology. So what are we showing here? On the upper left and right, voltage against time and current against time. The voltage is like the height of the water, and the current's like what's coming out of the can. I don't have 3 volts, it's simple. Well, that doesn't surprise me because over time, as the water level drops, there's less water coming out of the hole. So there's less charge kind of going through the system. Where is it going? It's going through, in this case, there's a little, I don't know if you can see this from there, a little resistor. It's just wire wrapped around a coil. It's an old Radio Shack, 50 ohm resistor. I think the important thing is look at the big graph on the right. I'm measuring the height of the water in the can versus what's coming out of the can, voltage against the current. So this is measuring versus time, but you can see if you saw that the graph plots the points up on the right corner first and then drops down. But it's a nice line. I mean, what would Ohm have said about this? I said so, so 150. So that was kind of interesting that the pressure pushing the water out of the can is kind of very predictable here. Linear things. Not everything in life is linear, but this is. Okay, so far? I'm going to kind of shorten this up. What if I take this out of the circuit? It's just a little wire and put in something else, like how about a little incandescent light bulb? Well, what do we know about incandescent light bulbs besides they're pretty hard to get these days? But these are small ones that aren't too. All right, so let's take a look, and the scale is going to be a little off, but let me fill the can with water again. Oh, wait a minute, switch has to go there. I was going to say that was too easy. All right, so I'm refilling my can with water. I'm almost through. All right, can's full of water, nothing's happening. So I'm going to say collect data. I know the scale's going to be a little off. And I think I'll let this go for 10 seconds. I wasted time here. But let's see if I can't stretch this out a little bit more and expand this so we can see a little bit more. All right, that's good enough. Whoa, that's very different. Now, when they did this, or when they do this, you can see the light bulb right at first. Not a surprise. This current's making a little lamp light up. What happens over time? Bulb gets dimmer. What's the graph showing on the right? Well, more voltage is more current is more voltage. But it's not linear. Is that a big deal? Maybe not. why might those two behave differently? One's called a lamp, one's called a wire. At least there might maybe some interesting discussions about. Here, once you drill the hole, you know, I'm not changing the diameter of the hole as the water comes through, but something is changing the ability of that light bulb to conduct electricity. What's the thing we're not talking about? The fact that the temperature is changing the behavior of the thing. Like, I better stop there. I'm late. Going to go home. I had a couple of other demonstrations related to this, but inevitably teaching ninth graders, you know, they wanted to try other things as a conductor. So someone had a hearing, a ring, or this or that, and someone, especially ninth graders, always say, "What if I put my fingers there?" Go for it. It's only 5 volts, nothing. So that led to discussion about, well, like your body is a conductor or an insulator. And I had a little device called a lie detector where if you put a probe between two non-invasive fingers, it could measure very, very precisely the resistance here, the galvanic skin response. Man, is this thing sensitive. It doesn't detect whether you lie or tell the truth, but it detects whether you're sweating or not. And I was going to bring that in, and I realized, brain glass dried up. I knew I was getting to be last in line. Boy, is that a fun thing to talk about, electrical resistance of a human body part. Amazing how it just blow in your palms. So can you imagine boarding school kids, ninth graders with a lie detector kind of thing? The one question I found didn't have any sexual implications. The one question I would ask sometimes, but really I thought, wow, that's a good. Do you like yourself? Do you like yourself? And almost every case, you would bounce around on scale to think of whether you think you like yourself. I mean, I could think of a lot of other questions that scales no computer, but that wasn't part of it.
Thank you. Oh, I'm sorry, you have a question.
Another point you make is the elements in the body. You point out that it takes 50 milliamps current to stop your heart. The resistance in your body, arm to arm, is like, okay.
Yeah.
So it takes a lot of voltage to get it. And I can get an estimate for where these voltages are.
I mean, if you actually measure the resistance across normal minus sweating right now, it's like that's the 100,000 ohms. No, it's not like 5 ohms.
Yeah,
But their instruments sense enough to maybe change the sweat.
then I know that song is awesome.
But not one we probably want under age.
Yeah, great. They test the battery guy before it.
Anyways, just wanted to say good afternoon. Look, as Barry just said a few minutes ago, I'm the only thing standing in the way of you guys going home, so I realize that. I'm not going to talk for more than a couple minutes here. But I just wanted to say, I thought this was a great meeting. I really enjoyed it. I wish we would have more of these, both sides of the river. I wanted to let you know about 3 things. The first thing is, you are all welcome and encouraged to please come to meetings in New Jersey if you'd like to. Right now, you can join us for free, and it's going to be that way for the next couple of years, I think. The only way to go through our website. So our website is njaapt.com, or not org, sorry. And if you go on, you can register for any of our meetings, and you become a member for free, and you'll get all of our emails and all that kind of good stuff. But we have a bunch of events. We probably do events monthly. We have workshops. I just had a workshop at my school last weekend. 2 weekends ago, before that, we had another one, another part of New Jersey. We kind of move around, and we have a momentum workshop coming up in 2 weeks in central New Jersey as well. And we have a bunch of other events come up later on in the year as well. There's a demo night coming up and such. But anyways, if you're interested, take a look at our website. Would love to have you guys join. And as Jeremy said, perhaps we will be, doing a joint meeting down the road. I think that would be a lot of fun to pursue. So, we'll, hopefully look forward to doing that. The other reason why I want to get up here and just say a few words was, how many of you guys in here teach AP Physics? So there's just a few of you in here that had AP Physics. So I just wanted to let you guys know that there's a lot of changes coming to AP Physics starting next year. And if you're not aware of that, you should be aware of it. And I just wanted to call your attention to that. What's the biggest changes actually are, well, all the courses are changing in terms of their assessment. Some of them are changing in terms of their content. But AP Physics C is probably going to see the biggest change because the content is going to stay roughly the same, but the assessment is changing drastically. So instead of having the last like 40 or 50 years, 2 90-minute exams, one for mechanics, one for E&M, now it's changing to 2 full 3-hour exams. And they're going to be on 2 separate days, according to Trevor Packer. That's, and some of the information is already up there. If anyone's interested in hearing any details, I'll be happy to talk to you about it. I am not an official AP person, so I can't speak for AP, but I'm an AP reader. And anybody else here an AP reader? I know Kathleen is, because that's how Kathleen and I know each other. Okay, great. So, I would encourage, if you are ever thought about doing some incredible professional development, even if you're a college professor, in fact, especially if you're a college person, the AP program, the College Board needs AP readers for physics. We're the guys and girls who actually grade the AP exam. It's a 1-week kind of, for 7, 8 straight days, you grade exams. It's horrible, it's grueling, it's nothing you'd ever want to wish on your worst enemy. But we have a lot of fun. It's like physics summer camp. We have a lot of fun with each other, and we get to know each other really well. And I've got friends all over the country because I've been doing it for about going on 10 years now. And it's the best professional development you ever have. And you will learn so much about the way physics is being taught in so many different areas. And you will come back and you will more than likely hug your students, because you'll realize how good things are in this part of the world as compared to other parts of the country when you read some of the stuff that you then come in front of your face. So, but if anyone's any interested in knowing anything more about that, feel free to just catch me on the way out or whatever. But you can apply for it. There's a desperate need for readers. We really want more physics readers to come, and the reading is always the same time every year. It's in the early June, and used to be in Kansas City. Now it's going to be in Tampa, at least for the next probably a few years. And it's all expenses paid, this type of thing. So if you're interested, and plus, if you need hours, you get about 60 hours, I think it is. You get a certificate for about 60 hours. Something. No, you get a certificate. Like it's a true like PD hours certificate. So you do it twice and you satisfy 2 or 3 times you satisfy your requirements.
When in early June, like the first week of June, type of early June, or?
Second week of June, they moved it. Now it's the second week. Yeah, it's a problem. That's one of the issues, is that a lot of us are still in school.
Yeah.
But now that second week, fewer people are in school. But I would always have to miss a week of school. Usually school districts, I find, are pretty supportive of it because it is such good professional development. And you become, I'm such a better AP Physics teacher in so many ways than I am now than I was 10 plus years ago. Simply because now I see how it's done. I see all the inside. You get all the inside information. You get to tell the kids all the secrets a lot of times, and it's a very, very valuable experience. So I would encourage it. So I don't want to take up any more of your time. You didn't come here to hear me talk, so but I just want to thank you guys for being gracious hosts with me as well. And I hope to see you in New Jersey sometime. And that's it. That's fine.
Can you be a certified teacher, or you need to be a college?
You need to, if you're at the high school level, you need to be a current AP Physics teacher when you apply. But sometimes when you apply, it might take a few years before you get accepted. I don't know why there's such a lag. Some of it's demographics. If you're a teacher from the Northeast, you're probably going to wait longer than if you're a teacher from Wyoming. It's just the way to do it, right? But as far as the collegiate level, I'm not sure. I don't know what the requirements are. I think if you're a college professor, they'll just take it like that because they really want a mix of people. You're welcome. Thank you.